Today we're going to be talking about continuity, which is what it sounds like. A function is continuous if there's no breaks in the graph. If you can trace a graph without lifting up your pencil, then it's continuous. If it's not continuous, it's discontinuous, and usually that happens at a specific point. So this would be an example of an infinite discontinuity because there's an asymptote. This is a jump discontinuity. We'd have to lift up our pencil to go from here to here. And then we have a point of discontinuity. So we're going to determine whether the graph is continuous or discontinuous, and if it's discontinuous, which type of discontinuity and the x-coordinate. So this one is clearly discontinuous. It has a jump discontinuity. Okay, and that's going to occur when x equals 1. This one, there's no breaks in the graph, so this one is continuous. This one is discontinuous. It has a point of discontinuity. And that happens when x is equal to 2. The mathematical definition of continuity has 3 conditions that have to be met. So a function is continuous at a point C, 3 things must be true. The function has to have a value at C. If there is a hole or an asymptote, then it would fail that first condition. The second is that the limit as x approaches C must exist. So if there's a jump, then it's not continuous. So it has to approach the same thing from both sides. Last is that that function value has to equal the limit value. This says all of that in one statement. F of C is the function value, the limit as x approaches C of f of x is the limit value, and they must be the same. So we're determining from the definition of continuity whether these are continuous. Now, it's pretty clear looking at the graph, it's not. But where does it fail in the continuity definition? So I'm just going to kind of do this step by step. So does f of 2, because we're looking at all these at 2, f of 2 exists. That's about 1/2. The limit as x approaches 2 does not exist because it's not going to the same thing from both directions. So it passes the first part, but it fails this. So this is not continuous because the limit does not exist. Our next one here, does it have a function value at 2? It does. Does it have a limit value at 2? It does. It's going to the same thing from both the left and the right. So the limit is 2. However, those are not the same. So this is discontinuous because f of 2 does not equal the limit as x approaches 2. So it has a limit, it has a function value, a limit, but the third part doesn't pass because those things are not the same. Again, graphically it's really clear that that's discontinuous. It's just how do we use the definition to confirm that. Another graph. So f of 2 does not exist. So it fails right from the bat. F of 2 does not exist, so this is discontinuous. Now we don't have the graph, so this is a little bit trickier. We have to use our analytic methods to figure out if this is continuous or not. So first, is there a function value? Yes, there is. According to the piecewise, it's 3. The limit as x approaches 2. So this function is 2, at 2 is 3, for everywhere else is this. So the limit as we approach 2 is going to be dictated by what this graph is doing. Okay, so I'm going to look at the limit as x goes to 2 of x squared minus 4. For these limits, we just evaluate. So I'm going to evaluate at 2. So 2 squared minus 4. 4 minus 4 is 0. So it has a function value, it has a limit value, but these are not the same. So this is discontinuous because f of 2 does not equal the limit as x approaches 2. Our next one, we have a function value of 4. Now we want to look at the limit as x approaches 2 of x squared minus 4 over x minus 2. Well, I can't just plug 2 into this because we get an undefined, but that does not mean the limit doesn't exist. And in a few class periods, we'll learn how to find this limit, but for right now, we can use the graph. So we're going to graph that equation. So I'm just going to do open parentheses x squared minus 4 over x minus 2. I'm just going to do a zoom standard. And it may be surprising, but this graph looks like a line. Well, we're interested in 2, so I'm going to trace to 2. Now when I trace, we see it's undefined there. But if I go a little bit to the left and a little bit to the right, if we look at those numbers are approaching 4. So we can say that that limit, it's going to the same place. This limit is 4, which means this graph is continuous. Okay. For our parabola, f of 2 is going to be 2 squared plus 3 times 2 minus 1, which is 9. The limit as x approaches 2, well, we just plug it in again, so we're still going to get 9. So this one is continuous, and of course it's continuous. It's just a parabola, so we're good. Okay. So we're going to investigate some functions. So we're going to investigate x minus 1 over x minus 1. So we're going to go ahead and graph x minus 1 and x minus 1. Making sure to put the top and the bottom in parentheses. I don't have to graph it to know where the point of discontinuity is. The point of discontinuity is going to occur at where it makes the denominator 0. So when x equals 1, we have an issue. So now we're going to look at what the limit is as we approach 1. So I'll trace to 1. And it's undefined, but if I go to the left and to the right, we're going to 1. So I can redefine this using a piecewise. So I'm going to say this is fine. I'm good with anything as long as x isn't a 1. If x is a 1, then we have a problem. This is discontinuous there. But if I essentially plug the hole with 1, because that's what the limit is 1, so then I want the function value to be 1. So now this is continuous because it has a function value and a limit value that are equal at 1. So I'd like you to try this one on your own and see if you get the same conclusion. So you can pause the video and go through there and see if you get the same thing I get. So for this one, we're going to graph it. The point of discontinuity is going to be at 3 because that's what makes the denominator 0. When we graph this and trace to 3, again, the graph looks continuous. If we look to either side of 3, it looks like it's approaching 5. So I can redefine this as a piecewise with x squared minus x minus 6 over x minus 3, as long as x doesn't equal 3, but when it does, we'll make that equal to 5. Again, I encourage you to try this one on your own and see if you get the same thing. So you can pause it and come back. There's going to be a point of discontinuity when x is equal to -2. When we graph it and trace to -2, again, nothing there, but if I go to the left and to the right, it's approaching around -4. So we can redefine this. We're good with this for all values except for -2. When it is -2, we'd like to plug the hole with a -4 to make this a continuous function. And we'll do one more of these. So we have x cubed minus 8 over x minus 2. So there is going to be a point of discontinuity when x equals 2. When we graph it, this is what we get. Trace to 2. And look at our values. So at 1.96, it's 11.8, and then it's 12.7. So the limit appears to be about 12. So then this can be redefined. X cubed minus 8 over x minus 2 when x doesn't equal 2. When it does equal 2, plug the hole with a 12. Okay, now we're looking at a piecewise function that's already written for us, and we're going to find the value of k so that we have a continuous graph, and then we're going to graph it. So it's going to have a function value. We've got a line here, a parabola here. It's going to be continuous here. It's going to be continuous here. The issue is at 2. We need them to go to the same place. So this one I can't change. So I'm going to look at where that one is going as it approaches 2. To do that, I can just plug in 2. So 2 squared minus 2, 4 minus 2 is 2. So what needs to happen is this one also needs to go to a y value of 2 when the x is 2. So I'm going to make a limit equation. I need this limit to also equal 2 in order for it to be continuous. So as I plug in 2 for x, this is going to be 2 times 2 plus k. This is 4, so I subtract 4 to get -2. So my k is -2, which makes this equation here 2x minus 2. Then we're going to graph it. Our boundary line is at 2. When it's less than 2, it's 2x minus 2. So it's going to be that line there. When it's greater than 2, it's the parabola. So when I plug in 2, we get 2 here. When I plug in 3, we get 9 minus 2. So at 3, we're at 7. 1, 2, 3, 4, 5, 6, 7. And then it's just going to continue up from there. We'll do one more of these where we're going to find R and P. And then I'm not actually going to graph it. So I'm going to find these values. This time I have 2 points that I need to worry about. We have a boundary at -1 and we have a boundary at 1. So when we want to make this continuous, I have to consider both of those. So when x is equal to -1, I need these two things to go to the same place. This one I can't change. So let's look at where that one's going. So that's going to be 2 times -1 plus 1. So -2 plus 1 is -1. So I need the second equation to also go there. So I need the limit as x goes to -1 of 3x plus r to also equal -1. So I'll plug -1 in for x. So we have a -3, we're going to add 3, so r is going to be 2. So that's our first value. Now our second area of concern is when x is equal to 1, I need these two equations to go to the same place. So now I know what r is. R is going to be 2. So I need to find the limit as x goes to 1 of 3x plus 2. Well, that's going to be 3 times 1 plus 2, which is 5. So I need this last equation to also go to 5 when x is 1. So we're going to make the limit as x goes to 1 of the square root of 2x squared plus p to also equal 5. We'll plug 1 in for x here. So we're going to square this. So we're going to have 2 plus p equals 25, which means p is 23. So this would be continuous on all of the graph. And that is continuity.